To calculate the correct wire size for a 220 volts residential subpanel, several factors must be considered, including the voltage drop, conduit length, desired current, and the material of the wire. A common formula used for voltage drop calculation is voltage drop equals 2 times K times L times I divided by D, where K is the conduit constant, L is the conduit length in feet, I is the current in amps, and D is the wire size in circular mils. The value of K for copper is typically 10.9. The National Electrical Code, or NEC, sets guidelines for the maximum allowable voltage drop. For feeders and branch circuits, the NEC recommends a maximum voltage drop of 3%. To determine the maximum voltage drop allowed for a 240 volt system, you multiply 3% by 240 volts, which equals 7.2 volts. Therefore, the voltage drop on a 165-foot conduit run should not exceed 7.2 volts to comply with the NEC guidelines. Now let's calculate the minimum wire size needed to provide 60 amps of continuous power over a 165-foot conduit run while staying within the 7.2 volts voltage drop limit. The formula for wire size in circular mils is D equals 2 times K times L times I divided by voltage drop. Plugging in the values, we have D equals 2 times 10.9 times 165 times 60 divided by 7.2. This simplifies to D approximately equals 29,944 circular mils. Referring to standard wire size charts, the nearest standard wire size to 29,944 circular mils is #4 AWG copper wire. Therefore, a minimum of #4 AWG copper wire is needed for the installation. It is important to note that this calculation is based on specific parameters, including a 240 volt system, a 165-foot conduit length, a desired current of 60 amps, and a maximum voltage drop of 7.2 volts. Always consult the latest edition of the NEC and local electrical codes, as well as a qualified electrician to ensure compliance and safety. Factors such as ambient temperature, the number of current carrying conductors in a raceway, and specific equipment requirements can affect the appropriate wire size. Remember that using undersized wire can result in excessive voltage drop, which can cause appliances and equipment to malfunction or operate inefficiently. It can also lead to overheating of the wires, creating a potential fire hazard. Conversely, using oversized wire can increase the cost of the installation without providing any significant benefit. In addition to voltage drop considerations, it's essential to select a wire size that is suitable for the ampacity or current carrying capacity of the circuit. The ampacity of a wire is determined by its size, insulation type, and installation conditions. The NEC provides tables that list the ampacity of various wire sizes and types under different conditions. When selecting a wire size, ensure that its ampacity is equal to or greater than the maximum current that the circuit will carry. This is typically the rating of the circuit breaker or fuse protecting the circuit. Furthermore, the type of insulation used on the wire must be suitable for the environmental conditions in which it will be installed. For example, some insulation types are designed for use in wet locations, while others are suitable for high-temperature environments. The NEC provides information on the types of insulation that are appropriate for different applications. It's also crucial to consider the method of installation when selecting a wire size. Wires installed in conduit may have a different ampacity than wires installed in free air. This is because the conduit can trap heat, reducing the wire's ability to dissipate heat. The NEC provides adjustment factors that must be applied to the ampacity of wires installed in conduit to account for this effect. In summary, calculating the appropriate wire size for a 220 volt subpanel requires careful consideration of voltage drop, ampacity, insulation type, and installation method. The NEC provides detailed guidelines for selecting wire sizes that are safe and effective. Always consult the latest edition of the NEC and a qualified electrician to ensure that the installation meets all applicable requirements. Let's revisit the key concepts to ensure a thorough understanding. Firstly, the voltage drop formula, voltage drop equals 2 times K times L times I divided by D, is used to determine the voltage drop in a circuit. The conduit constant, K, is a value that depends on the material of the wire. For copper, K is typically 10.9. The conduit length, L, is the length of the wire run in feet. The current, I, is the amount of current flowing through the wire in amps. And the wire size, D, is the cross-sectional area of the wire in circular mils. Secondly, the NEC recommends a maximum voltage drop of 3% for feeders and branch circuits. This means that the voltage drop in a 240 volt circuit should not exceed 7.2 volts. Thirdly, to calculate the minimum wire size required for a given application, the voltage drop formula can be rearranged to solve for D. This gives D equals 2 times K times L times A divided by voltage drop. Plugging in the appropriate values, the required wire size in circular mils can be determined. Fourthly, once the required wire size in circular mils has been calculated, a wire size chart can be used to determine the nearest standard wire size. It's important to choose a wire size that is equal to or greater than the calculated value. Fifthly, in addition to voltage drop considerations, it's also essential to ensure that the selected wire size has sufficient ampacity for the circuit. The ampacity of a wire is determined by its size, insulation type, and insulation conditions. The NEC provides tables that list the ampacity of various wire sizes and types under different conditions. Sixthly, the type of insulation used in the wire must be suitable for the environmental conditions in which it will be installed. Some insulation types are designed for use in wet locations, while others are suitable for high-temperature environments. The NEC provides information on the types of insulation that are appropriate for different applications. Seventhly, the method of installation can also affect the ampacity of a wire. Wires installed in conduit may have a different ampacity than wires installed in free air. The NEC provides adjustment factors that must be applied to the ampacity of wires installed in conduit to account for this effect. Now let's delve deeper into some of the factors that can influence wire size selection. Ambient temperature can have a significant impact on the ampacity of a wire. As the ambient temperature increases, the ampacity of the wire decreases. This is because the wire has a harder time dissipating heat at higher temperatures. The NEC provides correction factors that must be applied to the ampacity of a wire to account for ambient temperature. The number of current carrying conductors in a raceway can also affect the ampacity of a wire. When multiple current carrying conductors are installed in the same raceway, the heat generated by each conductor can raise the temperature of the other conductors. This can reduce the ampacity of the wires. The NEC provides adjustment factors that must be applied to the ampacity of wires installed in raceways with multiple current carrying conductors. Specific equipment requirements can also dictate the wire size that must be used. Some equipment manufacturers specify the minimum wire size that must be used to connect the equipment. These requirements must be followed to ensure that the equipment operates safely and effectively. It's also important to consider the type of load that the circuit will be serving. Circuits that serve inductive loads, such as motors, may require larger wire sizes than circuits that serve resistive loads, such as heaters. This is because inductive loads can cause voltage drops and current surges that can damage the wires. In addition to the NEC, local electrical codes may also have requirements that must be followed. These codes may be more stringent than the NEC requirements. It's important to consult with a local electrical inspector to ensure that the installation meets all applicable requirements. Let's consider a few examples to illustrate the application of these principles. Example 1. Suppose that a circuit is being installed to supply 20 amps load in a dry location with an ambient temperature of 30 degrees Celsius. The circuit will be installed in conduit with 3 current carrying conductors. What size wire is required? Firstly, determine the required ampacity of the wire. In this case, the required ampacity is 20 amps. Secondly, consult the NEC ampacity tables to determine the ampacity of different wire sizes. For example, #12 AWG copper wire with type THHN insulation has an ampacity of 30 amps at 30 degrees Celsius. Thirdly, apply any applicable adjustment factors. In this case, the NEC requires that the ampacity of the wire be reduced by 80% when there are 3 current carrying conductors in a raceway. This reduces the ampacity of the #12 AWG wire to 24 amps. Fourthly, compare the adjusted ampacity of the wire to the required ampacity. In this case, the adjusted ampacity of the #12 AWG wire, 24 amps, is greater than the required ampacity of 20 amps. Therefore, #12 AWG wire is sufficient for this application. Example 2. Suppose that a circuit is being installed to supply a 40 amps load in a wet location with an ambient temperature of 40 degrees Celsius. The circuit will be installed in free air. What size wire is required? Firstly, determine the required ampacity of the wire. In this case, the required ampacity is 40 amps. Secondly, consult the NEC ampacity tables to determine the ampacity of different wire sizes. For example, #8 AWG copper wire with type THWN insulation has an ampacity of 40 amps at 30 degrees Celsius. Thirdly, apply any applicable correction factors. In this case, the NEC requires that the ampacity of the wire be reduced by 0.88 for an ambient temperature of 40 degrees Celsius. This reduces the ampacity of the #8 AWG wire to 35.2 amps. Fourthly, compare the adjusted ampacity of the wire to the required ampacity. In this case, the adjusted ampacity of the #8 AWG wire, 35.2 amps, is less than the required ampacity of 40 amps. Therefore, a larger wire size is required. Fifthly, repeat steps 2 through 4 with larger wire sizes until a wire size is found that has an adjusted ampacity that is equal to or greater than the required ampacity. In this case, #6 AWG copper wire with type THWN insulation has an ampacity of 55 amps at 30 degrees Celsius. Applying the temperature correction factor, the adjusted ampacity of the #6 AWG wire is 48.4 amps, which is greater than the required ampacity of 40 amps. Therefore, #6 AWG wire is required for this application. In conclusion, calculating the appropriate wire size for a 220-volt subpanel is a critical step in ensuring a safe and effective electrical installation. By carefully considering voltage drop, ampacity, insulation type, installation method, and other factors, it's possible to select a wire size that will meet all applicable requirements. Always consult the latest edition of the NEC and a qualified electrician to ensure that the installation is done correctly.